Okay. So, this one we have seen that Pf is equal to Pb plus Pr, all the derivations we have seen, right, that your Pf minus Pb is equal to actually Pr. So, Pf is equal to Pb plus Pr, this we have seen. This is actually line termination is resistance, these are the different conditions. Now, second is that when line is terminated, your line termination your in impedance. So, in the general case of a line of characteristic impedance Zc terminated in an impedance Z, then we can write I is equal to 2 upon Z plus Zc Vf, because when line was your this thing we have derived when it was terminating in the resistance, that it was I is equal to 2 upon R plus Zc Vf, and here your V is equal to 2 R upon R plus Zc into Vf. So, instead of R you replace R by Z, because line termination in impedance. So, you assume that impedance is Z. So, this equation directly you can write, one is equation 48 and this one equation 49, right. So, this one you directly you will get from equation 48. In equation 48 you replace R by Z, then I is equal to 2 upon Z plus Zc into Vf. This is equation 57. Similarly, in equation 49 when line termination in resistance R, it was 2 R upon R plus Zc, but in this case it is terminated in an impedance Z. Therefore, V is equal to replace R by Z, it will be 2 Z upon Z plus your Zc into Vf, or V is equal to, you can define tau into Vf, where tau is called the refraction coefficient or transmission factor or simply coefficient tau, right. What we will do throughout this chapter, we will use tau all the time as refraction coefficient, right. Thus, for voltage wave tau, this thing tau is equal to 2 Z upon Z plus Zc. So, in that case we can write that the from this equation, if Z is equal to 0, then tau will be 0, right. So, and if Z is and your theoretically, that means theoretically this value actually will vary from your in between 0 and 2 depending on the relative values of Z and Zc, right. Or alternatively, this equation we can write Vf is equal to Z plus Zc upon 2 Z into V. So, Vf is equal to Z plus Zc upon 2 Z into V. Now, this V is equal to you got 2 Z upon Z plus Zc. Similarly, this I also you replace you know that V relationship between your Vf and If, right. So, in the case of Vf is equal to If into Zc. So, if you substitute If into Zc, so I will become 2 into Zc upon Z plus Zc. So, that term for the it is the refraction coefficient tau when 2 Z upon Zc for the voltage. I am making it for you, just hold on, I'll make it for you. For example, this I is equal to your equation from it is equation 57, right. I equal to your 2 upon Z plus Zc into Vf, right. But you know Vf is equal to If into Zc. Therefore, I is equal to 2 into Zc upon Z plus Zc into your If, right. Here we have made V is equal to 2 Z upon Z plus Zc Vf. Here we have made I is equal to 2 Zc upon Z plus Zc. This term, this one we have taken for voltage, refraction coefficient for voltage actually, and this term we can say we can make tau I is equal to 2 into Zc upon Z plus Zc, right. That means, for the current refraction factor is your what you call tau I. If voltage it is 2 Z upon Z plus Zc, and for your current refraction factor will be 2 Zc upon Z. It is not shown here, but I think it is understandable to you, right. So, this thing, so tau I is equal to 2 Zc upon Z plus Zc. If you add these two tau plus tau I, if you try to add this one, it will become 2, right. If you add tau plus tau I, that is your 2z upon z plus zc plus 2zc upon z plus zc, that is actually is equal to 2 z plus zc divided by z plus zc. So, this one will be cancelled and this is equal to tau plus tau I is equal to 2. Tau is the for voltage, I did not write it is tau v, I have simply written tau, it is for diffraction coefficient for the voltage, right. So, tau plus tau I will be 2. So, that means this your what you call this tau actually varies between 0 and 2, that is for each case tau I also varies in between 0 and 2, and theoretically similarly tau for the your what you call for the voltage diffraction coefficient also varies in between 0 and 2 depending on the relative values of z and zc, right. Similarly, this Vb is equal to z minus zc upon z plus zc into Vf, because just hold on, we have seen that your for when it was your resistive circuit, right, resistive this one, when line termination in the resistance, we have seen Vb is equal to R minus Zc by R plus Zc. This is equation 51, right. So, from 51 and in this case line is terminated in impedance Z. So, in this case you replace R by Z. Therefore, your Vb will be Z minus Zc divided by Z plus Zc. It is already these equations are derived. Only you have to what you have to do is you have to replace R by Z, that is all, right. Therefore, this Vb, that is your reflected voltage or your backward wave, right, that Z minus Zc upon Z plus Zc into Vf, this is equation 62, or we can make Vb is equal to rho into Vf. So, this is equation 63. Rho is the reflection coefficient, or sometimes we call reflection factor, right, reflection coefficient. Therefore, for voltage wave rho is equal to Z minus Zc upon Z plus Zc, right. Rho can be positive or negative, it depends on whether Z is greater than Zc or less than Zc. This is equation your 64, right. Of course, rho can be positive or negative depending on the relative values of Z and Zc, right, this one. For example, when the line is terminated with its characteristic impedance say Z is equal to Zc, if Z is equal to Zc, then rho is 0, then your rho will be 0. So, there will be, so rho is 0 means there will be no reflection voltage. So, Vb is equal to 0 then if rho is equal to 0, right. So, thus your Vb is equal to 0 and Ib is equal to Vb by your what you call that Zc. So, as rho Vb is 0, therefore, Ib also will be 0. So, in other words, the line acts as it is infinite long line, right. So, in that case you have to imagine the line is actually infinite long. So, when the line is terminated in an impedance that is larger than its characteristic impedance, I mean if Z greater than Zc, right, if Z greater than Zc, then rho is positive, that means Vb is positive and Ib will be your negative. This is your common phenomena, right. If rho is become Z minus Zc upon Z plus Zc, you will take, when you will try to find out that Vb is positive, then your what you call that your current, that one will be your what you call that your negative, that Vb is positive, then Ib is negative, and opposite, if Vb is negative, Ib will be positive. All this relationship actually we have seen previously, just go through those equations. Therefore, the reflected surge consists of increased voltage and reduced current, right. And if you see the figure, if you look into this figure, right, look, this is your diagram, this is the voltage Vf, now this is your Zc and line is terminated impedance Z, right. This is up to this is before arrival at termination. So, generally we are considering a step function Vf and If, right. R and resistance and conductance is neglected, and this wave is moving from left to right. This is Vf, this is sending end voltage, and this is If, the current. Now, this is before arrival. When it is arriving, when on arrival at termination, right, in that case what will happen, that Vb is your what you call backward wave is positive and it will move to this way. Now, it is right to left it will move. So, that is why when it is right to left it is moving, V is equal to Vb Vf plus Vb, that means it is increasing, right, because on arrival at termination the back reflected voltage Vb or backward wave, this is positive, that means whatever Vf was there, then Vb is this much. So, if you Vf plus Vb, so V is equal to Vf plus Vb, it is moving from right to left now, right. And for the current on arrival at termination, that Ib is negative. If Ib is negative, that means if you just add these two, this one and this one, ultimately it will go down. So, that this is your I is equal to now If minus Ib, right, because as Ib is negative, if you take direct negative value, then If plus Ib. When we are taking I is equal to If minus Ib, means this magnitude has been taken positive in this equation. Otherwise, you can write If plus Ib, but Ib is negative. But for your understanding, here it is given I is equal to If minus Ib. So, this Ib will be subtracted from this. So, this is the current wave. Now, it has decreased magnitude, it is moving from right to left, right. So, this is before arrival at termination. On arrival at termination, this is the reflected wave magnitude Vb, and this is the reflected current wave, right. And finally, after arrival at termination, I mean when it is moving from right to left, it is V is equal to Vf plus Vb and I is equal to If minus Ib. So, this is hopefully understandable to you, right. That means, this is actually that through that from figure 4 we have seen that surge consists of increased voltage and reduced current as shown in figure 4. I shown you the figure 4. Now, on the other hand, when line is terminated in an impedance that is smaller than its characteristic impedance, when Z greater than Zc. If Z greater than Zc, then Vb is negative from the same equation and Ib will become positive, just opposite. Thus, the reflected surges consist of a reduced voltage and increased current as shown in figure 5. Now, when Z less than Zc, I mean this one, when Z less than Zc, that means rho is negative, this is negative, that means Vb will be negative and Ib will be positive. So, this is the diagram, that it is Zc and Z again. Now, this condition is when Z less than Zc, when less than Zc, right. So, before arrival this is same as before. Now, when on arrival at termination, Vb will be negative. So, this is Vb, right, and current will be positive. So, this is Ib. If one is negative, another will be automatically positive. If Vb is negative, current is positive. If Vb is positive, then current is negative, right. So, on arrival at the termination, so this is your voltage wave, it is moving from, this was moving from left to right, distance is increasing, right. So, an arrival at terminal, this one, now this Vb will be now reflected back at the arrival of terminal, this is Vf and this is If, but now Vb is negative Ib. So, when it is moving to the your right to left, I mean from this side to this side, when it is moving, then V will be Vf minus Vb. Here Vb is negative, but this magnitude, for your understanding, it is Vf minus Vb, means this Vb will take plus here, such that Vf minus Vb. So, this magnitude, this one is getting reduced. So, voltage magnitude will reduce, but current, that Ib is positive. So, here it is moving now from right to left, I mean this direction right to left. So, it is showing here. So, current will be added. So, I should be equal to If plus Ib positive. So, this way that your after arrival at your what you call at termination, that means it is reflected. So, this is actually, it is in figure 5, that is why analysis of travelling waves when Z less than Zc. A is the circuit diagram same as before, and B is the voltage and current distributions, right. Hope this will be understandable, there should not be any confusion, right. Next one is, now Similarly, thus the reflect this one we have seen in figure 5. Now, if ZS and ZR are defined as the sending end and receiving end Thevenin equivalent impedance. Suppose if you define ZS is the sending end side and ZR is the receiving end side Thevenin equivalent impedance, right. I think power system analysis course regarding this Thevenin equivalent, those who have taken this course or seen that lecture, this equivalent Thevenin how to one to get in a power system, I explained there in detail, right. So, here not putting it again, right, but Thevenin equivalent impedance how to obtain details I think I explained there. So, if ZS and ZR are defined as the sending end and receiving end Thevenin equivalent impedances respectively, the sending end reflection coefficient is, in that case it will be rho s will be ZS minus ZC upon Z plus ZC using the same formula, equation 64. You replace Z by ZS one case and receiving end side replace Z by ZR, right. So, Z minus ZC upon Z plus ZC, right. So, that rho s, the sending end reflection coefficient will be then rho s will be ZS minus ZC divided by ZS plus ZC. This is equation 65. Similarly, at the receiving end the reflection is your it will be receiving end impedance is ZR, here it is ZR, therefore, rho r will be ZR minus ZC upon ZR plus ZC. This is equation 66, right. So, this is understandable, I believe this is understandable, not much difficult one, only understanding is required. Now, note that wave travelling back toward the sending end will result in new reflection as determined by the reflection coefficient at the sending end rho s. Just now we have seen this one rho s we have seen this one, right. Furthermore, note that the reflection coefficient current is always the negative of the reflection coefficient for voltage, right. So, in this thing this is always we have seen that your whenever you will take that your reflection coefficient for the current is always negative of the reflection coefficient for voltage. Previously, when we are doing this, just you try yourself, you will find it will be just negative of this. I mean that is why if voltage is positive, current is negative. If voltage is negative, current is positive. Now, take a small example. Small example is that consider equation 60 and 62 and verify that I b is equal to rho I f and tau is equal to rho plus 1. So, I have to go to equation 60 and 62, just hold on, right. This one, this is your equation, just hold on, this is your equation 60 and 62, this is equation 62 and just hold on 61, this is 61, this is 60 and 62, this is equation 60, this is equation 60, tau is equal to 2z upon z plus zc, this is equation 60 and this is equation 62, right. So, you have to prove that I b is equal to rho I f and tau is equal to rho plus 1, that is the voltage your reflection coefficient, right. I did not write tau v suffix, but tau is equal to rho plus 1. So, since we know I f is equal to V f upon Z c and we know I b is equal to minus V b upon Z c, this we know, right. Therefore, V f is equal to, we know Z c into I f, this is your V f is equal to Z c into I f and V b is equal to minus Z c into I b, right. Therefore, substituting them into equation 62, that means in equation 62 you just substitute, right. This is your where equation 62, just let me see, actually so many slides are there, but anyway directly we can write here it is 62, this equation you substitute there, equation sub 62. So, if you substitute, then you will find minus Z c into I b is equal to rho into Z c into I f, right. Therefore, you will get I b is equal to minus rho into I f, right. That means, if rho is positive, then I b is your what you call that negative, right, and if rho is negative, then I b is positive, just vice versa, that voltage and current. since rho is equal to z minus zc upon z plus zc, we know this, then both side you add 1. So, rho plus 1 is equal to z minus zc upon z plus zc plus 1 is equal to, you can write 2z upon z plus zc, but we know 2z upon z plus zc is equal to tau, hence tau is equal to rho plus 1, equation 68. So, this is proved, right, that tau is equal to, and IB is equal to your minus rho IF. Here verify that IB is equal to minus, one minus sign I think I have missed, it should be minus, right, it should be minus. So, that is your what you call that IB is equal to, so this thing are very simple, these things are very simple, right. So, next is your what you call an example, take an example. Example, this is example 4. Suppose a line has a characteristic impedance of 400 ohm and a resistance of 500 ohm, right, its ZC is 400 and R is 400, right. So, assume that the magnitudes of forward travelling voltage and current waves are 5000 volt and 12.5 ampere respectively. Determine the following: 1. Reflection coefficient of voltage wave, reflection coefficient of current wave, backward travelling voltage wave, voltage at end of the line, refraction coefficient of voltage wave, backward travelling current wave, current flowing through resistor and refraction coefficient of current wave, right. So, these 8 quantities you have to obtain from the given data. These are very simple one, right, very simple one. So, first one just see, I will write, but this is basically when line is terminated at resistance R. So, we know example, the first one we know rho is equal to R minus ZC upon R plus ZC. It is given R is equal to 500 ohm and ZC is equal to 400 ohm. So, 500 minus 400 by 500 plus 400 is equal to 0.1111, right. And therefore, in B it will be minus, in B it has been asked that you find out reflection coefficient of the current wave. So, just now we have seen in general that if rho is for voltage, if it is positive, current it will be negative. So, it will be minus R minus ZC upon R plus ZC. So, minus of same thing 500 minus 400 by 500 plus 400 is equal to minus 0.1111 we have taken up to 4 decimal place. We know VB is equal to rho into VF, this also we know. So, VF is equal to 5000 volt, because it is given the forward travelling wave voltage and VF is equal to 5000 volt and IF is equal to 12.5 ampere, this is given, right. Therefore, VB is equal to rho into VF. So, it is 0.1111 into 5000, that is 555.555 volt, up to 3 decimal place it is taken. Now, V is equal to then VF plus VB. So, it will be you 5000 plus 555.555. So, it will become 5555.555 volt, that means your that VB is positive. So, when it is reflecting back, the voltage is increasing, right. Or V is equal to, I mean for this thing, if you make the cross check, V is equal to 2R upon R plus ZC into VF, this is equation 49. Same thing, here we got directly by multiplying rho, but another equation is there, equation 49, that also you can write V is equal to 2R upon R plus ZC into VF, that is actually 2 into R is equal to 500 divided by 500 plus 400 into VF. VF is this voltage, this 5000 volt, right, into 5000. So, 555.555 volt, same thing, right. This one also you can use. Now, tau is equal to, you have to find out the reflection coefficient for the voltage. If you see tau is equal to 2R by R plus ZC, right. So, in that case your 2R upon R plus ZC, that is your 2 into 500 divided by 500 plus 4, that is 1.11 or 0.111, right. Just hold on, just find out that equation, just 1 minute, right. The tau is that your this thing, the refraction coefficient, because it is something like a light, right, some reflection will be there, some refraction will be there. So, tau is the refraction coefficient. So, but philosophy here it is different. So, tau, this equation is coming, actually here we are writing 2z upon z plus z60, but previously that z here the line is terminated by resistance R, it will be 2R upon R plus ZC. So, this one actually refraction coefficient tau is equal to 2R upon R plus ZC. So, it is 2 into 500, R is 500 by 500 plus 400, that is 1.1111, up to 4 decimal place I have taken the refraction coefficient, and IB is equal to your minus your VB upon ZC, right. So, VB we have got this 5555.555. So, substitute here, no, VB backward voltage, sorry, VB we got 555.5, this is VB, right. Therefore, IB is equal to minus 555.555 on 400. So, minus 1.3889 ampere, or other way you can do it, IB is equal to minus rho into IF, and rho you have got 0.1111, so minus 0.1 into 12.5, because IF is given 12.5 ampere, this is IF. So, if you do so, you will also get minus 1.3889 ampere. I mean, the way you want you can do it, right. So, tau is the refraction factor, just hold on, right. That means your, anyway later we will see that refracted volt, later we will see. So, that means all the quantities straightforward, you can get it. This one actually, this one tau actually, this is your refraction coefficient, right, such that when we listen to this there will be no problem, refraction coefficient. So, that means and I is equal to your V by R, right. So, that means that last one it has been asked, that is so G that it has been asked that current flowing through resistor, that what is the current flowing through resistor, this is G part, right, and refraction coefficient of current wave. So, I is equal to actually V upon R, V you have got 5555.555, right, when this thing, and R is equal to 500. So, 11.111 ampere, and for the current tau is equal to 2 ZC upon R plus ZC. So, 2 into 400, ZC is 400 divided by 500 plus 400 is equal to 0.8889. So, that means this is this one, it is 1.111 refraction coefficient, this is for voltage, this is for voltage, right, and this refraction coefficient, this is refraction coefficient, this is refraction coefficient for current, right, this is for current. Now, I showed you, no, I showed you that tau plus tau I, it has to be 2, it has to be 2. So, if you see there that here this is for voltage, it is 1.1111 plus this is for current 0.8889. So, it will basically it will become 2, if you add this, right, it will become 2. So, that is why that this is your tau is equal to, there is a refraction coefficient for the current. So, total should be your what you call the 2. So, that means refracted, if you take that for that this thing, this refracted your refraction coefficient for voltage, not shown here the diagram or computed, right, it is increasing, whereas the current in the case it is decreasing. If one decrease, another will increase. If one become reflected also, if one become negative, another will become positive, and the refracted case, if voltage increase, current decrease, if current increase, voltage decrease, because that condition should hold good, that refraction coefficient for voltage plus refraction coefficient for current must be equal to 2. Thank you, we will be back again.